Okay, one thing you should always keep in mind about the work is that work is not a vector. It is not a vector, it doesn't have a direction. You cannot talk about the work in that direction or the one in the other direction, etc. It's a number. It can be positive or negative. And whenever you are talking about the work, now you have to always talk about work done by a force. So if you are talking about the work done, each force is doing the work. Without a force, we cannot talk about the work. By a force on an object. So if you want to talk about the work done, the force is always acts on an object. Without something that the force acts on, again, you cannot even talk about the work, the force, so you cannot talk about the object. So you always have to be careful about the work done by a force on an object. Now in this case, there are several things you can talk about. Let's say I'm in the elevator is moving up, you are just fixed on us. I am exerting a force on this keyboard, so I am doing the work on the keyboard, which is positive, it's going up. There is also gravity. Gravity is exerting a force on this keyboard, which is going downward, so the work done by gravity on this keyboard is negative. There is also a force that this keyboard exerts on my hand. The keyboard is exerting a force on my hand, which is pointing downward, and we are being displaced upward, so the force done by the keyboard on my hand is negative. When we study gravity, we will also say that okay, the keyboard is also exerting a force on Earth. The Earth is not being displaced significantly, so there is no work done by the keyboard on Earth. So you always have to pay attention to which force are you talking about when you are talking about the work done. And by which force, what is exerting this force on what? So you have to have these two objects. One object should be exerting the force, the other object should be exerted by a force. Okay. And work is never a vector. So you don't put a vector sign and don't show its direction. It doesn't have a dimension. It can only be positive or negative.
Static friction, it means the object is no moving.
Okay.
So I'm exerting a force, but the object is no moving. Now, the same way I should expect that when two objects.
But before you go on, what is the work done by each one of these forces? So in the question, you can say, okay, here is the book. I'm pushing the book, but I'm not pushing it strong enough to overcome the static friction. So I'm exerting a force, there is a static friction force acting on the book is not moving. So what is the work done by my finger on the book? Zero. The displacement is zero. What is the work done by the static friction between the book and the table? Again, zero. There is no displacement, no work.
So I should expect that also in the same way, if two objects, if it's possible, that case is possible, two objects are moving very quickly, like I was explaining earlier, using my hand to stop something, I should expect that it is possible for two forces to oppose each other and they will make displacement.
Okay, so I'm exerting very strong forces. Each one is enough to overcome the friction force, But the two forces are in opposite direction, so there is still no displacement. So what is the work done? Yeah.
So it means that in the moment where, I hold the ball and there's no displacement, the work done is zero.
No. You see, this is the question that your friend has. He holds the ball and stops the ball instantaneously. So that the ball does not move after he holds it. Right? So the ball is not moving, so we are saying that in principle the work should be zero. But there is a kinetic energy change. So how come this law that we wrote before, that change in the kinetic energy should be equal to the total work done on the object? How can that be true? There is no displacement, so there is no work. But the kinetic energy of the ball, it changed. There was a non-zero change, and the total work seems to be zero.
But sir, in this case, what you just said is an assertion. Is an assertion that the change in kinetic energy has to be the same as the work done. So it's possible that in certain cases, where there is a change in kinetic energy, there is no work done.
Well, you see, we drive this relation assuming Newton's laws. So as long as Newton's laws are correct, this has to hold.
But sir, do you understand my scenario I just explained as in...
Now, let's look at this example. Let's look at this example. Okay, so this is moving. He just holds it instantaneously. So I just keep my hand fixed. It just drops down. And so at the instant that there is contact, at the instant that I exert this force, it stops immediately. My hand doesn't move. So there should be zero work done. There is no displacement. Now the problem here is, let's say, this instantaneously. What do you mean instantaneously? There is a change in delta V. And instantaneously just means delta T is equal to zero. In the idealized case. But this means this is infinite. But this means the force that you have to exert is also infinite. Which cannot be. So in real life, what is actually happening is, okay, you're exerting a large force, but a finite one. But for in real life, the force will be finite. It can be huge. And if you just take this object, throw it on the wall, well, the wall will not move. So it will just hit it, it will bounce back, and for an instant it will stop. There will be and the moment that it hits, at that instant it just stops. But even in this case, what is actually happening is that there is this force. The force is not infinite, it's just huge. Since it is huge, it just stops the ball quite fast, but not instantaneously.
But if I can only define acceleration, it means that I shouldn't be able to define the force, because force is mass times acceleration.
No, I define acceleration.
I mean, if I can indicate I kick the ball, I set the ball into motion, the ball at rest. If I set it into motion, at the point in time, from 0 to 100.
Okay, we have to always talk about measurements and the precision of measurements. So what you are actually saying is that the time it takes for this object to stop after making the collision is zero. You can never measure zero time. The only thing you can say is that it will be below a given value. It will always be below a given value. Nevertheless, it will be non-zero.
So, should I say, perhaps, Newton doesn't really explain things that come to very infinite, it is not able to explain.
Well, we have never ever seen such an object. We never observed such a system.
Yeah, because I realized that changes, the velocity of the ball changes from 0 to a certain velocity.
In a finite amount of time.
Exactly.
And Newton's laws are even valid there.
But how are they valid? Because at that point, if I want to calculate the answer, I can only do it 5 times.
No, I mean, the thing is, you cannot measure time because you don't have enough measuring instruments. You might not have it, but we have it. They exist. And we can measure very small time intervals. We can record them, we can watch videos of them, and that is what we see. The object, when it hits this wall, it doesn't stop instantaneously. It stops at a very short amount of time. And Newton's laws are still valid. We never ever observe an object that stops from some finite velocity to zero velocity at zero time. We never made that observation. For every system that we observe, there is always, we could measure how long it takes for it to bounce back. And the time interval is finite. It takes a finite amount of time for any object to stop from a given initial velocity. This is observation. And we never have seen anything that contradicts this observation. Okay. Any other questions? Which one? Newton's second law. What do you mean? Okay, so the total force is zero. This is the work done by the normal force. Whatever your values are, whatever your and you just can put it here. This is the work done on the object by the weight of the object. We know the weight, we know the displacement, just put it over here. Now what this tells me that, applying the second law, it tells me that the normal force and the weight, they have equal magnitudes, they are just pointing in opposite directions. That's what Newton's second law tells me. Because of here, the acceleration is zero, so the total force has to be zero. So if the total force is zero, the normal force and the weight, they just point in opposite directions. They have their equal magnitudes. If that is the case, this term, the work done by my hand, and this term, the work done by the weight, they have equal magnitude, just opposite signs. If this is positive, this is negative. Okay.
So we can we say that there is a force in the positive?
Okay.
And according to that force, should we have an acceleration?
Okay. So, according to Newton's second law, just don't ignore the word the net force. The acceleration is determined by the net force acting on the object. Now, the net force is the sum of all the forces, not just a single force. In this example, there are two forces acting on this. The force that I am exerting, that's the normal force, and the force of the gravitational force, the weight of the object. There is two forces. Each one of these forces, we can calculate the work done by each one of these forces separately. There's no problem with that. But the total force should be zero. Although I am exerting a force, the total force has to be zero because the acceleration is zero, so I just deduce that the weight and the normal force that I exert, they have to be equal in magnitude. That is one thing. The second thing, when we calculate the work, I am doing positive work on the object, weight is doing some negative work on the object. The total work done, which is equal to the change in the kinetic energy. The total work done is just the sum of these two, which is zero. Each one of them, they are not zero, but the sum is zero. Each one of these forces, they are non-zero, but the total force is zero, and hence the acceleration is zero. Other questions?
Maybe not entirely related to the course, but you said that you don't see any object that stops instantaneously. Can you generalize this to say that you don't see any object that changes velocity instantaneously?
Sure.
So what about electron states? Electron states, they're discrete, right?
Okay.
They don't have any in-between states, so basically, but they move from one state to another, they change their velocity instantaneously.
No.
No?
No.
How do they change that? How do they change it?
Continuously. Smoothly. But I mean, discuss that in the quantum physics for after the course. Even there, everything is continuous. In physics, nothing changes, is continuous. Almost.
I understood that by holding this net growth is zero.
Okay.
And if I take it to upward with constant velocity, again, the net growth is zero.
Sure.
But there is the difference, I think. It's because of potential energy.
What kind of a difference?
I think they are not the same. Just field.
Well, it's just a chain of coordinates, it's reference frames. You can just hold it that book like that and go for a reference frame moving at constant velocity.
I think in this situation, my force is equal to rate. But in this situation,
They're also equal. As long as the acceleration is non-zero, the acceleration is zero, the weight and the force that you exert should be equal in magnitude and opposite in direction. So it doesn't change whether it's moving at constant speed or not. Other questions? Well, you see, there's always, whatever the case is, the work done is always equal to force by delta R. You can imagine quite complicated forces, quite complicated systems, etc. In every case, you have to identify what is the force and what is the displacement. As long as there is you know the force, you know the displacement, this is the expression of the work done. Whatever the system is. This is the displacement of the point that the force is being exerted. Okay, let's take an example. Let's go back to our roller coaster example. But this time, let's imagine that we have a complicated roller coaster. And let's just imagine that at the top part, it is almost a circle with radius R. And at the top part, it has a speed V. And here it has a speed V0. And let's just assume that this height is H. And we don't yet know potential energy of gravity, etc. We don't know it, so we are not allowed to use it. So what should be the speed V0 so that it will not fall at the top? Now we have already solved part of this question. We have said that V should be larger than or equal to square root of GR. We already know this much. Now the question is, what should be V0?
That will be external forces that will change a lot. For example, engine maybe.
There's no engine, there's no friction. There is no force, there is a weight, those are the only forces you have. example, in this problem, if you want to calculate the acceleration at any one of these points, because at this point, you first have to calculate the normal force, you have to calculate the weight, you have to calculate the component of the weight along this curve, etc. That will give you the acceleration, and it will be a really tough job. Calculate the acceleration, calculate how long it takes to come here, and just calculate the change in the velocity from this point to that point. It will be really tough. It's not impossible, you can still do it, but it's kind of not unnecessarily complicated. There is a much more easier way to using the work done. We already know that the change in the kinetic energy of the object will be equal to the total work done on the object. What are the forces acting on the object? Where is the gravity? What else? There is also the normal force. What is the work done by the normal force? The problem is we don't know the normal force, so if we need to calculate the work done by the normal force, then again it will be quite complicated. But what is the work done by the normal force? The normal force, if the normal force is equal to the weight, then the object will not be accelerated. It's definitely accelerated, at least we can say that the velocity has changed its direction, to say the least, so that has to be some acceleration. So what is the work done by the normal force? Why? True. Right. At any point, we say that the normal force is perpendicular to the surface, but the object is moving tangent to the surface. So if the object is moving tangent, the normal force is perpendicular to the surface, then the displacement is 90 degrees all the time. And of course, in this case, the normal force is constantly changing. It's really a motion with a variable force. But nevertheless, if you take a very small, if you look at the very small displacement, each one of these small displacements will be perpendicular to the normal force at that time, at that position. So the work done will be zero. So the total work done is nothing but the work done by gravity. Is the weight of the object constant? The weight is the same. So since we already know what the work done by a constant force is, so what is the weight? Well, let's say this is R delta R. Scalar product with delta R. What is the direction of the weight? So is the work done positive or negative? The work done should be negative. The angle between the weight, let's say this is the weight, and delta R will be just larger than 90 degrees. So this is our weight. This is delta R. And this is the H. So the work done by gravity is mg times delta R times cosine of, let's call this angle theta. So cosine of cosine. Well, there's no minus sign here. You see, when we define the scalar product work done by gravity is equal to weight dot delta R. Now, the scalar product is defined as the product of the magnitudes. The magnitude of this force is mg. The magnitude of this displacement vector is called delta R. We have the vector side. Times cosine of the angle between the two. So, which is cosine theta plus 90 degrees. Plus pi over 2. Now, cosine theta plus pi over 2 is nothing but minus sine theta. So now here comes the minus sign. Minus mg delta r sine theta. But delta r sine theta, if you just look at this triangle over here, it is nothing minus mg times h. This is the work done by gravity. And we also know that this has to be, this is the total force. So So this is equal to the change in the kinetic energy of the object, which is 1 over 2 m times v squared minus 1 over 2 m v0 squared. This is equal to minus mgh. So we can just cancel the m's, or v0 squared should be equal to v squared plus 2gh. And if the object is not to fall down, this should be larger than or equal to gr plus 2gh. Now in this problem, we don't know how long it took our object to go from the bottom to the top. We don't know what the acceleration were in the intermediate state. Nevertheless, we know that the velocity at the top and the velocity at the bottom are related by this relation. This is not even a motion with constant acceleration. The acceleration of the object was constantly changing. The question was this one. What should be the initial velocity such that when the train reaches this point, it will not fall down? We had already determined that the speed at the top should be larger than the square root of gr, if it is not to fall down. And we have found the relation between this v0 and v function by just using the work done, the total work done on the object. Ask that question in a moment. Let's look at the work done by a variable force. Now, the normal force is a force that changes as the object is moving. So let's first discuss this one and then come back to your question. Let's just imagine that we have this object. It is moving from here to here along this trajectory. It can be an arbitrary trajectory. Then why does it move like that? There might be many forces acting on the object, and the total force acting on the object will just cause it to move, follow such a weird trajectory. For example, you can just take this one and move it around with your hand. So we are exerting different forces at different times, such that it follows this weird trajectory. And let's imagine there is one force that you are interested in. And of course, that force will be a function of the position. It can be the force that you are exerting on the object. So as the object is moving just like this, at this instant you are exerting your forces downward, at the next instant, and when it reaches this point, you will be exerting in this direction, etc. The force will be changing from point to point. So we cannot use this previous expression, the work, will not be just the force times displacement, because that expression is valid only if the force is constant. And in this case, it is not constant. So we cannot directly use this expression, calculate the displacement, multiply it with some force. But we can still do one trick. We can divide this path into very small segments. We can divide it into very, very small segments. Eventually, we will take the limit that those segments will go to 0. Now, within each one of these segments, the force will be constant. It will not be changing. Well, it will be changing, but the change will be negligible. So we can just ignore the change. Within each one of these segments, the force is constant. So we can calculate the work done, let's say, in the segment as my object is moving in this segment, or let's say in this segment over here, the displacement is, let's just call it dr. Let's show it by a small vector d. dw will be equal to f at the point r dot dr. Now this is the work done by the force F as the object moves through this dr. It's just a very small segment. Now if you want to calculate the work done on my object, I just sum all of these. So the total work done by the force F will be just the sum of these dWs. This is basically the idea of a changing force. Now let's apply this to the normal force case. We have this roller coaster. Now when my train is over here, the normal force is in this direction. When my train comes here, the normal force is in this direction. When it is over here, it is in this direction. So the normal force constantly changes its direction. Now if I want to calculate the work done by the normal force, I first divide my trajectory into very small segments. For each one of these segments, I have the displacement. Let's say here, this is my displacement, and this is the normal force. The displacement is along the surface, parallel to the surface, but the normal force is perpendicular to the surface. So dW from this part it is n dot dr. But since both of them are perpendicular, this is 0. The same thing is true for this very small segment and also for this very small segment, for any of the small segments. So although there is the normal force, which is constantly changing, but since it is always perpendicular to the displacement, it doesn't do any work. The same thing holds for uniform circular motion. Let's say we have this mass M carrying out some uniform circular motion. There is this force due to tension. There is a center of force. But the center of force is always perpendicular to very small displacements in very small amounts of time. This is always 0. So the work done by the tension is again equal to 0. Tension doesn't do any work. It creates acceleration, it causes the velocity vector to change, but it doesn't change the speed. So it doesn't change the kinetic energy. Two masses. I will leave that alone. Repeat, continue. Okay, so we have two masses on the same string. They are doing uniform circular motion. Are they? Compare what about the work by the normal force by the tension will be 0. The rest will be a homework. Other questions? Well, that one, okay, so this is what you're asking. Well, that's a nice example. So let's just assume we have a table. On this table, there is a hole at the center, and there is a rope passing through it. You have an object doing some uniform circular motion. There is a rope that passes through, and you exert a force on that. Let's suppose that initially the speed of the object is say v0, the force is f0. And you just pull it down by exerting a larger force, by increasing the force. Let's just set it out. So this is the table. There is a hole on it. So there is a mass carrying out uniform circular motion. We are ignoring friction. Now the tension is created because you are holding the string with your hand from below the table, and then you just pull the table that will pull the string down by that. So now the object will be doing some circular motion, but at a smaller radius. So what will be the mean speed of the object? How fast? So initially, the velocity, the speed is v0, the length of the circular orbit is r, and the force or the tension is f0. Finally, the speed is v, the radius of the circle is r minus l, and the force is f. So what is v? Circular motion.
So you subtract the force you apply from that force, and then because if you know the new distance, the new r, so using the relationship F equals mv squared over r, now you know r, you know the mass, and then you know by subtracting the force you apply from the initial centripetal force, you have a new force. So you use the force, the radius, the mass to find.
Okay, what is the work done? Basically, it will amount to what you say. What is the work done by the force? Why? You see, you are holding the string, and you are pulling it down. The force is pointing downward, the displacement is downward. You calculate the work done by the force considering the displacement of the point at which you are exerting the force. So you are pulling it down. So you don't get the motion of the ring. You are doing the work on the string. You are pulling it down. So you are doing a pointing work. Now the first question is, you are not exerting a constant force. If it had been a constant force, you would just have F times the displacement, that would be the work done. So what is the force that you should exert on the string? How does it change? How can we calculate it? You see, the force that we exert is nothing but the tension on the string. tension on the string is what creates the circular motion. So the tension or the force when the radius is, let's say, small r, this has to be equal to m times the speed when the radius is small r divided by r squared, v squared. This is how the force changes as a function of r. Of course, now there is a problem. What is v of r? The velocity when the radius of the ring is just r. What is it? With r squared, this is, okay, if r is the force, the magnitude of the force when the ring has radius r. V of r is the speed of the mass when the ring has a radius r, the circle has a radius r. It was almost correct. So we know the force in terms of an unknown function v of r. Then the problem is we have to calculate the work. So we are kind of stuck.
Is it this speed of force?
True.
Speed of force is acceleration in circular motion r times. Acceleration is circular motion is v squared over r, so v squared over r squared.
True. This is the correct expression. But nevertheless, we don't know v of r. Now, of course, you can try to proceed by this, but still it will be quite difficult with the techniques we know. We will learn some other quantities in a couple of weeks, which will allow us to calculate this v of r, although we don't know what f of r is. So we will be able to calculate this one, put it over here, that gives us the v, and that will allow us to calculate the work. But at this level, I'm afraid we are stuck over here. So this is something that we should look for in the future.
In order to see some change in velocity, speed, let's say, we need a force opposite the. We need a force to slow down the object we are.
Okay.
That is not the particular velocity.
Well, you see, when you are pulling it down, if it is not necessarily perpendicular to the velocity anymore, but if you are pulling it down, it means your mass is moving towards the center. So there is a very small component of velocity towards the center. F dot v will not be zero in this case when you are pulling it down. Sure. You can make it very small, but nevertheless there is an angle. Any comments on this one?
Okay, if we multiply both sides r, when f goes the distance r.
Now, r is not the distance that they move.
Okay, what if what you take and r? You take
R is the radius of the string.
okay.
So it is not the displacement.
Okay, but I'm saying we are pulling the by r, so we are making the total 0.
No. R is not how much you pull. R, the way we define the R is not how much you pull. So you have to use a different symbol for that.
When you show the previous
arbitrary force that you like. So we were trying to find FOR, but can it be this arbitrary? Is that what the question will be? Okay, any last minute questions? Okay, I will have your question in the room. Somebody else? Right after the course. There are still some questions. The F will be the equal to the tension, and the tension will be something more. Okay, see you on Tuesday.